All right, welcome back. We're here one more time solving the same crankshaft problem, looking for the velocity at point C. And in this case, we're going to be using absolute motion analysis to solve the problem. So the general method for using absolute motion analysis is to draw a triangle over our system. In this case, we're going to put a line from A to B, from B to C, and also from A to C like that. And we'll label each of these sides just with a small letter that's like opposite the angle. So small a will be across from big A, small c will be across from big C, and small b will be across from big B. And then the next thing that we want to do is identify which side is going to be experiencing a change in linear length as the angle is changing. So this is our angle here. Let's actually label it as theta. And as theta is increasing, basically it's, in this case, it's rotating to the left. So it's going to be opening up. Well, member AB is not going to be changing in length. Member BC is not going to be changing in length. But this side here, B, is actually going to change in length as theta opens up there. So what we need to do is we need to write an expression that links that side to the given angle. And in most cases, especially with crankshafts, we're going to be using the law of cosines. So with the way that I've identified theta here and labeled the sides, we can write the law of cosines in two different ways. But be really careful when you're applying the law of cosines, especially if you pull the formula out of a textbook, because depending on how they've labeled their sides and which angle they're talking about, these letters get all mixed up. So make sure you take really good care in determining that you actually have the right expression. If you need to, maybe you have to look at your diagram and switch the order of the letters around just so it matches what you actually have in your problem. And not every problem is going to be using the law of cosines as well to find this expression. For example, if you have problems that are like a ladder slipping down a wall, then in cases like that, you're actually going to have two sides of the triangle that are changing length as the one angle changes. It's a simpler problem because it's a right angle triangle, so usually you can get away with just simple sine or cos functions, which you can relate later than using a single angular velocity, but let's not worry too much about that. Let's just focus on the crankshaft problem right now, which does use the law of cosines to find the expression for side B here. Now, something that you might also want to do if the side that you're looking at is aligned with the x-axis or the y-axis, is maybe just change the label to the actual letter. So we might want to change B here just to make it a little bit more obvious about what the next step is. So if we relabel this as x, then if we want, we can come down here and replace these with the letter x as well. And the reason I do that is because for whichever version of the law of cosines that we choose, we're going to derive it twice with respect to time. And so if we have an x in here, it just makes a little bit more sense. When we have x, then we have dx dt is the derivative with respect to time, which is equal to velocity. And then the second derivative, so d squared x over dx squared, is equal to the derivative of the velocity with respect to time, which is just equal to acceleration. And when we're doing this, we are going to differentiate twice, and we're going to leave in theta as just a variable. We're not actually going to substitute in the value that we have for it. And the reason is for that is the initial expression here will have a theta in it. When we take the derivative of theta with respect to time, we're left with omega, which is our angular velocity. And when we take the derivative of angular velocity, that's the same as the second derivative of theta, which is angular displacement. And so that is d squared theta over dt squared, which is equal to d omega over dt, which is angular acceleration. And depending on the type of problem we have, like in this case, we have a constant angular velocity. And so when you take the derivative of the constant angular velocity, then the angular acceleration would be 0. Other problems, you might be given the angular acceleration as a non-zero value, and then you'd be able to work backwards to find out what omega is if you need to. But basically, as you can see, when we derive one of these expressions twice, it's going to get pretty messy, and it's always going to involve using the chain rule. But you'll see that in 1 second. So from there, once you've identified the expression, you can pretty much just plug in your values and then just plug and chug all the way till the end until you get an answer for the quantity that you're looking for. In this case, it's going to be VC. And just to make that as clear as possible, the x here, the quantity of x was what is changing over time. So as this shrinks in this case, that's going to equal the end speed here, which is vc. And as well as that speeds up, that's going to be equal to the acceleration of point C if you need that quantity. So let's use the second expression here, and we can move on with solving the problem. We're going to take this version of the law of cosines because x is already by itself on the left-hand side. If we were using the first one, we have an x squared term here, and we also have x here. So it's just going to be a huge mess trying to rearrange it to get to this expression, but we already have this one, so let's go with that. So we have x is equal to c, and c was right here. It's the small c, it's 0.2 meters. 0.2 times cos of theta. Again, we're going to leave that as a theta. We're not going to write the 30 degrees. Plus a squared. Well, side A was 0.5 meters. 0.5 squared minus c squared, which is 0.2 squared, times sine of theta all squared. And that is under the square root. Okay, we can simplify this a little bit. So we have x is equal to 0.2 cos theta plus 0.5 squared is 0.25. And we can bring in the 0.2 inside that bracket. So we just have 0.2 sine theta all squared. And then it's easier to work with this when we're doing derivatives to, instead of writing the square root sign, just to bring that brackets and raise it to the power of 1/2. All right, so let's take the time derivative of both sides. So on the left we have dx dt. And then for the first term, the derivative of 0.2 cos theta, 0.2 is a constant, so it stays outside, and the derivative of cos theta is negative sine theta, so we get negative 0.2 sine theta. Now that is the derivative of this thing, and when we take the chain rule, we have to take the derivative of the outside and the derivative of the inside, so we have to multiply it by the derivative of theta, which is d theta dt. Now for the next term, we're actually going to have to apply the chain rule more than once. So let's start with the whole thing. We need to take the derivative of basically this part, so we'll bring down the exponent. So we have plus 1/2 times everything that was already there, 0.25 minus negative 0.2 sine theta squared, and that's all to the negative 1/2. And then we need to take the derivative of the inside for the second part of the chain rule. So for the first term here, the 0.25, that will just be 0, so we don't need to write that. So really we need to take the derivative of negative 0.2 sine theta all squared. So to do that, we bring the 2 down, and there's a negative sign. So we become minus 2 times the inside, which is 0.2 sine theta. And then again, because of the sine rule, we have to take the derivative of the inside again. So now we're taking the derivative of this part right here. And the derivative of 0.2 sine theta is 0.2 cos theta. And then once more, because of this chain rule, it just keeps going. We keep zooming in and in and in. We have to take the derivative of theta one more time, so d theta dt. So basically, if you didn't get that, it's because with the chain rule, we always have to take the derivative of the outside of the function and then multiply it by the derivative of the inside of the function. But when we have to take the derivative of the inside, and then there's more things that are differentiable, it just keeps going and going and going. And in this case, we had to apply it 3 times until the whole expression is satisfied. So we can simplify just a little bit. We have this 2 here can cancel out with that 1/2. But keep in mind not to get rid of this negative sign. Then we can rewrite dx dt as vc, and then the next term is just negative 0.2 sine theta, and then we can rewrite d theta dt as omega ab. And it definitely is the angular velocity of AB that we're looking at, because as theta changes, it's the change in this angular displacement is the angular velocity of this member. It has nothing to do with the member BC. So watch out for that. And then the rest of the expression is all one big term. Don't forget that negative sign, so we can have it right here. And then let's write what we had on the top. It's going to be basically this section will be on the top, and this will be on the bottom because of that negative exponent. So let's write the top first. which is 0.2 sine theta times 0.2 cos theta times d theta dt, which is omega AB. And then we can write the denominator, which is the square root of 0.25 minus 0.2 sine theta all squared. Okay, let's give ourselves a little bit more room to work with here. And what we want to do in the next step is fill in the values that we have, that we know for sine theta and for omega AB. So VC is equal to negative 0.2 times the sine of 30 times omega AB. And if we look back at the original diagram, it was 25 radians per second. So times 25. And then in the next term, we have 0.2 sine 30 times 0.2 cos 30 times 25. That was radians per second. And in the bottom, we had the square root of 0.25 minus 0.2 sine 30 all squared. Okay, so this all simplifies to VC is equal to negative 2.5 minus 0.433 over 0.48989. And if we just come over here, we can simplify it further for VC is equal to negative 2.5 minus 0.88386. And lastly, we can just calculate that as VC is equal to negative 3.38 meters per second. And that negative sign indicates that it is just going to the left-hand side. So VC is equal to 3.38 meters per second to the left. So there we go. Let's drop a box around that. That is the final answer. That is the velocity of C when the crankshaft is in this exact position. And that is the same value that we got in the other 3 videos where we also solved this exact same problem with different methods.